conditional expectation second. So, based on our theoretical basis of conditional expectation from the given probability space, we have seen that we have defined a particular another sigma field or other sub sigma field which is a subset of the original sigma field in the original probability space, and based on this we have derived conditional expectation and conditional probability and hence conditional probability measure. So, today we are going to discuss few more results relating to this conditional expectation specially. As for example, we all know that from a given probability space, if we define a random variable, we know that sum of expectations or rather expectation of sum of random variables is equals to sum of expectations. So, the question is whether this kind of result is also true in case of conditional expectation, and we will discuss this theorem or this result and some other important results with respect to conditional expectation. The basic objective is that I will do some recap of definition of conditional expectation and conditional probability and probability measure, the formal definitions, and after that we will study a few properties of conditional expectation which are extremely important to understand the conditional expectation, and also a few theorems or few important results that we can derive when we deal with conditional expectation. Now, it is expected that these theorems should give analogous results when we deal with the simple expectation. So, let us start with a quick recap of the definitions. So, let omega script f and p be a probability space, and let us assume that B is any arbitrary but fixed subset of omega and B belongs to script f. Script f is the sigma field generated by the class of subsets of omega. Now, consider the class of events as B intersection script f, which is the set of sets B intersection A such that A belongs to script f, and we denote this by script f B. This class, so this definitely forms a class of events or class of sets. This class is a sigma field of subsets of B, because we are only looking at the subsets of B. Hence, B, so B is the biggest set, we can say a big one like omega. So, B basically plays the role of omega in a normal probability space, and this script f B, it can be shown that this is also a sigma field. So, B script f B is a measurable space. Now, once we have a measurable space, we can easily define a probability measure as follows. PB, we denote this by suffix B. PB of B intersection A equals to probability of B intersection A by probability of B on script f B if probability of B greater than 0. Now, only important thing is that to note that we have divided this probability of B intersection A by probability of B, because probability of B may not necessarily be equals to 1. So, that is the reason we normalize this. So, naturally it is easy to see that if we replace A by B, that means B intersection B, which is nothing but probability of B with respect to the measure PB, this would be equals to 1. That means this also ensures that B, this capital B, plays the role of omega in case of actual original probability space. So, now we can say that B script f B and PB is nothing but a probability space, and PB is the probability measure defined on this space. We call this PB as conditional probability measure given B, and we denote this by PB or P dot given B. Now, it is very easy to check that PB is non-negative, PB of omega equals to 1, and PB is sigma additive on script f. Because PB is a probability measure, it must satisfy all these three conditions, and fortunately it really satisfies these conditions. It is extremely easy to see. So, we can immediately say that we are very much confident to say that PB is a probability measure on omega script f. Thus, omega script f and B is a probability space. So, we have defined this conditional probability measure on omega script f. PB of A is called conditional probability of A given B, and PB dot, that means for any set belonging to script f b or script f is called conditional probability distribution on omega script f. So, these are the very natural consequence of the way we defined conditional probability measure. Then let us also recap the definition of conditional expectation. Let omega script f and p be a probability space, and we define script a as a sub sigma field of the basic sigma field script f. We assume x is a script f measurable function of omega whose integral exists, that is modulus of expectation of x is less than equals to infinity. Then defining phi of b as integral over b x dp for b belongs to script a. We can see that phi is the restriction of phi to sets of script a, and we denote this by phi given script a. So, naturally by Radon-Nikodym theorem there exists an script a measurable function y which is equals to d phi dp on omega, and we call this function as conditional expectation of x given script a, and we denote this by expectation of x given script a. So, now we know the definition, formal mathematical probabilistic definition of conditional probability as well as conditional expectation. Why I am calling it probabilistic? Because we have defined this entire thing from the original probability space. Now, it is also seen that y is basically defined by two conditions we have already discussed in a previous talk, but we are just doing a quick recap. Y is script a measurable, and integral of y dp is nothing but integral over b d phi given script a dp into dp for all b belongs to script a, which is same as integral over b of x dp. So, now we have defined conditional probability measure and conditional expectation from a standard probability space. So, the mathematical basis is well defined, and we are in a pretty good position to study conditional expectation and conditional probability further. So, let us first consider an example, a very simple example. So, assume that script a equals to collection of 4 sets only, b complement phi is a null set in this case, and omega, which is a subset of script f, and take capital X as indicator function of another set a, where a belongs to script f, but a not equals to b. So, we have taken a to be strictly non-identical to b. Then from the previous definition, we immediately have integral over b x dp equals to integral over b ia dp, because x is nothing but ia, indicator function of a, and which is nothing but probability of a intersection b, and we can write this thing as integral b over b expectation of x given script a dp just by the definition. Similarly, we can have integral over b complement x dp is nothing but probability a intersection b complement equals to integral over b complement expectation of x given script a dp. So, now this function is script a measurable. So, this must be of the form C naught IB plus C1 IB complement. C naught is a constant over constant, and C1 is another constant whenever the event belongs to script B complement. So, from here we can immediately write whenever omega, for every omega belongs to script A, we can immediately write expectation of x given script A equals to C naught. Then probability of A intersection B is equals to C naught into probability of B. So, C naught equals to probability of A intersection B by probability of B if probability of B greater than 0. Similarly, taking omega belonging to this B complement, we can immediately have C1 equals to probability of A intersection B complement by probability of B complement, provided probability of B complement is greater than 0. Thus, expectation of IA script A of omega equals to probability of A intersection B by probability of B if probability of B greater than 0, and this is equals to probability of A intersection B complement by probability of B complement if probability of B complement greater than 0. So, this gives us an example. This example also clearly shows that there is a relation that or rather it exploits the relation between probability and the expectation of indicator variable in defining or in elucidating the concept of conditional probability as well as conditional expectation. So, now let us consider a few properties of conditional expectation. First, assume that f star is a sub sigma field of script f. Initially we have used the notation script A, but just to make the readers acquainted with several notations, I have used a different notation here. So, let f star be a sub sigma field of script f, then expectation of x given f script f star equals to x almost surely if capital X is f star measurable. Also, if y is a constant, that is k almost surely, then expectation of y given f star equals to k almost surely, or we can write expectation of y given x equals to k almost surely. Now, in particular, we can immediately write, as a consequence of this above 1 and 2, we can immediately write expectation of 1 given f star equals to 1 almost surely. That means this is true for any constant, and expectation of Cx given f star equals to C into expectation of x given f star almost surely, provided modulus of expectation of x less than infinity and C is a constant. So, this is analogous, this expectation of Cx given f star equals to C into expectation of x given f star is nothing but analogous theorem of simple expectation, like expectation of Cx equals to C into expectation of x. So, whether we use conditioning or not, the same kind of result still holds. Again, if x1 is less than equals to x2 almost surely, then we can have expectation of x1 given f star is less than equals to expectation of x2 given f star, which is same as saying expectation of x1 given x equals to small x less than equals to expectation of x2 given x equals to small x. Again, expectation of x given f star greater than equals to 0 if x greater than equals to 0, modulus of expectation of x given f star is less than equals to expectation of modulus of x given f star, and modulus of expectation of x given y equals to y is less than equals to expectation of modulus of x given y equals to y. So, these are very simple theorems, and the proofs are very easy. If we just start with any side, maybe from the left hand side, and stick to the formal definition of expectation that we have already discussed, we will eventually be able to prove this. The proofs are extremely easy, so I am omitting this proof. Now, let's come to the one of the most important theorem in the area of expectation or conditional expectation. We all know that the additive property of expectations of random variables. Now, let's see what happens if we deal with conditional expectation. Fortunately, the same kind of theorem holds here is true in case of conditional expectation. So, let us formally state this theorem. If a and b are two constants that belong to the real line, and a into expectation of x1 and b into expectation of x2 is well defined, a into expectation of x1 plus b into expectation of x2 is well defined, then expectation of ax1 plus bx2 given f star, that is the conditional expectation or conditioning on this sub sigma field script f star, is equals to a into expectation of x1 given f star plus b into expectation of x2 given f star. That means, first if we conditioning on a particular sub sigma field, that is f star, and then try to find out the expectation of this linear combination ax1 plus bx2, this is same as, exactly same as a times conditional expectation of x1 plus b times conditional expectation of x2 conditioning on f star. Now, we can simplify, or a simplistic version of this result is expectation of ax1 plus bx2 given x equals to small x is nothing but a into expectation of x1 given x equals to small x plus b into expectation of x2 given x equals to small x. In particular, expectation of x1 plus x2 given f star is nothing but expectation of x1 given f star plus expectation of x2 given f star, if of course expectation of x1 minus plus x2 minus less than infinity, or expectation of x1 plus x2 plus less than infinity. So, just by putting a equals to b equals to 1, we get this one. So, let us prove this theorem. Let a belongs to script f star, then integral over a ax1 plus bx2 dp equals to integral over capital A ax1 dp plus integral over a bx2 dp. This is by additivity of integral. Now, if we recall the definition of conditional expectation, we can immediately write this quantity equals to integral over a into expectation of x1 given f star dp plus integral over a b into expectation of x2 given f star dp. Hence, we can say that integration over a capital A into expectation of x1 given f star dp and integration over a b into expectation of x2 given f star dp are well defined. So, since these two integrals are well defined, we can again apply the additivity theorem for integrals in order to get the final result, that is expectation of integral over a ax1 plus bx2 dp given f star equals to integral over a into expectation of x1 given f star dp plus integral over a b into expectation of x2 given f star dp. So, this gives us confidence that one important theorem which we know for simple expectation is also holds true for conditional expectation, and we have seen that many other properties of expectation holds true in case of conditional expectation. So far we have studied conditional expectation and probability, obviously conditional probability, and also discussed few properties of conditional expectation as well as one important theorem which gives us some analog version of the standard or the original additive property of conditional expectation, as for example expectation of sum of random variables. In this case we have taken conditional expectation which is equals to sum of conditional expectation of this random variables conditioning on a particular sigma field, and we have just generalized this thing. Instead of considering the sum of random variables, we have considered the linear combination of random variables using two or three constants. So, this gives us a very general idea and a feeling that we can probably extend the theorems that are true in case of expectation of random variables. We can easily extend